Okay, in this example we're going to do a couple of things that are slightly different. And one of those has to do with that we're reversing the role of the typical way that these kinds of distributed load problems come at us, which is usually, let's turn this upside down, impose a distributed force on the system and ask what are the concentrated reactions that happen. And instead, what we're going to do in this instance is look at a slightly different and realistic context. We have a foundation slab that is relatively rigid, and we've got two closely spaced columns that are creating concentrated loads, and we're asking what the distribution of those effects are onto the soil, or what the soil is pushing back to provide equilibrium onto our foundation slab. So the geotechnical engineer has suggested to us that the soil is such that we could consider the distribution or the variation of this soil pressure to be linear, right? So that's what we're posing. We don't know what the intensities are at either end, but we're assuming that there's a linear variation in between, and we're trying to figure out what those are, right? So that's the major change, two major changes. One, flipping the roles of what these load models typically look like, and then we're trying to figure out, this is the second part of that's new, is, well, what are these intensities that go along with this, right? So it is just a distributed load that we can work with. So when you go draw the free body diagram in this instance, we've got the two concentrated applied forces, and then we've got this representation graphically of these loads, or rather the resistance. And the intensity at the left is WA, the intensity at the right is WB. Now you're going to see that I have chosen to show this as two triangles. And the reason, rather than say a rectangle and a triangle, the reason why I did that is because I can deal with this one triangle really simply, and the other one also really simply, and each one will only be in terms of either WA or WB. If I do it as a rectangle, well, the whole rectangle will be WA, but this other triangle will be the difference between WB and WA, and that makes the math just a little bit messier, and I don't like to deal with messy math. So instead, I'm going to try to keep it simple, and this is one way to make it a little bit simpler to work with. Of course, we'll get the same answer no matter what we do. So, for instance, let's sum moments about point A. Let's take counterclockwise as positive, right? So we'll have 1/2 of WA times its base on the triangle, 1.8 meters, right? That's just the force itself. I'm going to call that whole force just capital A, right? That's going to be convenient later on. And it acts at, well, the centroid of that triangle, right? So that triangle is 1.8 meters along its base, so it's in that big fat portion, 1/3. Oh, that happens to be right also under the 24 kilonewton force. That's kind of interesting. It doesn't mean anything, but that's its effective or equivalent acting point. So its moment arm with respect to A then would be our 0.6 meters, right? And then plus, well, we got this other triangle, which is also 1/2 of its base times its height. Its height is WB, and its base is 1.8 meters from here to here, perpendicular to that height WB, right? And it's located also at a 1/3, 2/3 location, which will be then at 1.2 meters away from A. Now I don't know what it is vertically, and that skewness of the triangle would mess that all up. I don't know what it is, and I don't care, because that's not relevant to the sum of moments, because you know that effective force is acting through that centroid, and it's vertical in its orientation, so I don't really care vertically on the page where that centroid is located. Right? So we got the total force there would be 1/2 of WB times 1.8. That's what I'll call B. And then we got the moment arm of 1.2 meters. And then we got to take care of the 24 times and that's kilonewtons times 0.6 meters, and then minus 30 kilonewtons times its moment arm of 1.8 minus 0.3 or 1.5 meters, and we're going to set all that equal to 0. Right? So let's simplify that a little bit. We have, in effect, A times 0.6 meters plus B times 1.8 meters is going to be equal to all this other stuff. The 30 is easy. 30 times 1.5 is 45, right? Plus the 24 times the 0.6, that's 59.4 kilonewton meters. Okay? Now, that would be just one equation. Two unknowns, one equation. Well, we could also sum moments about point B, or we could sum forces in the y. I generally like summing moments, but for the heck of it, I'm going to sum forces in the y because I know my students tend to like that better. So we'll do that. We'll have 1/2 of WA times 1.8, or in other words, A, plus 1/2 WB times 1.8, that's plus B, and then we'll have minus 24 minus 30 is going to be set equal to 0. So in other words, we'll have another equation that is A plus B equals 54. And now we got two equations, two unknowns, and we can solve for those. Oh, hey, let's keep track of our units. Put that in there. That's kilonewtons. All right. So I'm going to repeat the equations here on the next page so that we have them all handy. We've got 0.6A plus 1.8B equals 59.4, and we have A plus B is equal to 54. Right, now the first thing I'm going to do is actually take equation 1, and I'm going to divide by 0.6 so that I end up with A plus, and then that would be 3b, wouldn't it? 1.8 divided by 0.6 is going to be 3b, equals, and then this last part, 59.4 divided by 0.6, is 99. Right? I did that because now I'm going to take, this was equation 3, and I'm going to take 3 minus 2, and that's going to be this one minus that one. So the A goes away. 3b minus b would be 2b, and that's going to be equal to 99 minus 54, which is what, 41, I think? No, it's not either. It's 45. Sure enough, 45. And so B, therefore, B equals then 45 divided by 2, or 22.5 kilonewtons. Huh. Well, that's interesting. Hey, what about the units? Well, remember, 59.4 was kilonewton meters, and 0.6 was meters. So when I divided through by 0.6, I was dividing through by meters, and I had kilonewtons. And we already had kilonewtons in the second equation, so I was subtracting like with like here. It does work, and it is important to pay attention to all that. And of course, now that we have this one, we know if A is 22.5, then we know that A equals 54 minus B, 54 minus 22.5, and that means A equals 31.5 kilonewtons. Right? Now that's not what we were asked for. Instead we have, well, A was equal to 1/2 of WA times 1.8 meters. So we now know that A is 31.5 kilonewtons, and so check this out. WA is going to be equal to 2 times 31.5 kilonewtons divided by 1.8 meters. The units matter, and they show up perfect to what we've got going on here. And that is WA represented the intensity of a distributed force, and the units show that exactly. And that has got to be that way. If not, we've made a mistake someplace. Right? Likewise, B was all this mess. No, we didn't have to do this, but see how much easier it was to solve this by hand when we finagled things around like this? It's really quite a bit easier to work with. And so we'll get 2 times 22.5 divided by 1.8, and that equals 25 kilonewtons. Only in a statics book would you get nice perfect numbers like this as your answers, right? But there you go. Those are the intensities of our distributed force that correspond with the distributed load that the soil is going to support those applied columns, right? WA is actually larger than the 25. That's kind of interesting here, and that's a little surprising. It makes me want to go back and say, well, it didn't really matter that I had set it up this way. This was still 2 triangles at work, so that's okay. Does that actually make any sense to me? Well, no, it doesn't actually, because we got the 30 over here. It makes me think I might have made a mistake. So let's double check our math here, right? 1/2 WA times 1.8, that is the whole base, got that. 0.6, got that. 1/2 WB times 1.8 times 1.2, that's doubled. Okay, so that's included there. Minus 24, I have a sneaking suspicion of where I've made a mistake. Nope, not yet. Oh, I do too know where I made a mistake. You saw it a long time ago, and you didn't say anything, right? I know where the mistake is. This is not 1.8. That is supposed to be 1.2. That's going to change this to be 2. It's going to change this to be 1. And that means B is not 22.5, but 45, right? And so that makes A go down to 9. Boy, that changes the values quite a lot, doesn't it? Times 9 divided by 1.8. That changes that to 10. And of course, this is now 45. So 2 times 45 divided by 1.8 is 50. And that's a lot more what I would have expected. Wow! Why was it you expected that? Well, because note, the 24 kilonewtons was about at the 3rd point location. The 30 was larger than the 24, and it was outside of this 1/3 point. It was closer to B. That all suggests to me that the effect of these loads are shifting a little bit over to the right. And so if that's the case, oh hey, you know, I could figure out where that effective centroid is located, couldn't I? 24 times 0.6 plus 30 times 1.5, that's the moment with respect to A, and divide by the 54 is an equivalent distance of 1.1, which is not halvesies at all, right? It's shifted over to the right. 1.1 divided by 1.8, that's 61% of the way to the right, and that's why we get this asymmetry, a little bit of the asymmetry in that 10 and 50, plus, you know, that we got 30 versus 24, and the 30 is shifted over to the right. So I did expect WB to be much larger, and it turned out that intuition was right. It helped me figure out the mathematical mistake that I had. And I'm not going to redo this video. You need to see how you figure out mistakes that you have, and how you know you've made a mistake.